Hello, I'm Emily Homin, and today, together with my colleagues, we proudly present the Electromyography-Driven AI Assistive System for Stroke Rehabilitation, or EDASR. This novel wearable platform is engineered to restore safe mobility and daily living autonomy to stroke survivors suffering from partial or complete paralysis. By fusing real-time surface EMG signal decoding, computer vision, radar sensing, and deep learning controllers, EDASR interprets residual muscle activity and environmental data to guide patient movement, proactively avoid hazards, and even automate everyday tasks via a unified smartphone application. Today, I'll walk you through the clinical motivation, system design, implementation, and validation that underpin this integrated neuro rehabilitation solution. Every year, over 15 million people worldwide experience a stroke, and roughly one-third of survivors are left with lasting motor deficits, such as hemiplegia or limb paralysis. These individuals face elevated risk of falls, special ulcers, musculoskeletal strain, and secondary injury complications that place enormous physical and emotional burdens on both patients and caregivers. Conventional assistive devices, rigid orthoses, passive bases, or bulk accelerators provide static support but lack the intelligence to adjust in real time to a user's own muscular intent or to dynamic environmental hazards. EDS-ASR addresses the critical shortfall by integrating a patient's own EMG signals with AI-driven context awareness using a truly adaptive responsive aid that literally moves when the user moves and stops when danger appears. Current rehabilitation aids fail in three fundamental areas. First, they do not detect or interpret the faint electromyographic signals emanating from residual muscle fibers, so voluntary neural drive cannot be translated into operative movement. Secondly, they remain oblivious to the patient's surroundings, hallways, thresholds, stairs, or moving obstacles, leaving survivors vulnerable to collisions and falls. Third, the broader assistive ecosystem is fragmented. Health monitoring platforms, e-commerce services for essential supplies, and emergency alert systems operate in isolation. EDSR unifies these functionalities into a single variable or wheelchair motor platform, seamlessly combining intent decoding, environmental sensing, and smartphone integration to deliver an end-to-end solution for safety, autonomy, and quality of life. Our EMG AI platform empowers users to convert faint muscle activation into intentional muscle commands with a neural network decoder. At the same time, integrated radar and stereo RGBD cameras continuously map the surrounding environment, detecting static obstacles, dynamic hazards, and changes in floor elevation. A central controller fuses these data streams to issue proportional actuation signals to either a soft exosuit or wheelchair drive motors, guiding quiet precise movements. Voice prompts and micro gesture commands, captured by an onboard microphone and miniature IMU, can trigger daily life automation such as ordering groceries, adjusting lighting, or calling for help, all managed through a unified smartphone interface. Whether the patient wears the module on the wrist, upper arm, thigh, or integrates it into a wheelchair chassis, ADSR adapts it to individual needs and living conditions. Our primary aim is to develop and validate a robust, economically viable assistive solution that deciphers voluntary muscle signals, perceives and mitigates environmental risk, and automates routine tasks, all to grant stroke survivors greater autonomy, safety, and dignity in their day-to-day lives. By combining cutting-edge biosignal processing with context-aware AI, EDASR strives to redefine the standard of care in post-stroke neurorehabilitation, moving beyond static support towards intelligent, user-centric assistance. To achieve this, we will deploy surface EMG electrodes on target muscle groups like biceps, triceps, quadriceps, or hamstrings, sampling signals at high spatial and temporal resolution. Feed these digitize signals into a convolutional neural network, CNN, trained on datasets from both neurologically impaired subjects and stroke survivors. The decoder outputs intended movement clusters with latencies under 1000 milliseconds. Copper-based radar-based frequency modulated continuous wave sensing and stereo RGBD vision to generate a real-time three-dimensional map of obstacles, drop-offs, and moving objects, and drive soft SOSU actuators or wheelchair motors proportionally, matching user intent or enforcing safety constraints, and finally integrate all telemetry and control information into a React native smartphone app that provides live dashboards, hazard alerts, grocery ordering shortcuts, medication reminders, and emergency call functionality. The EDAR system architecture comprises 5 key modules. For the EMG front end, surface electrodes connect to an analog amplifier and analog to digital converter, producing a clean digitized EMG stream for on-device inference. Perception module, a TI-AWR series radar chipset, and Intel RealSense D435i cameras work in tandem to detect obstacles, measure distances, and classify moving hazards. For the control unit, an embedded GPU or FPGA fuses intent and environmental data using an extended Kalman filter and decision-making logic to compute safe motion trajectories. For the actuation subsystem, soft exosuit cables with variable system tensioners or bustless DC wheelchairs motors apply proportional assistance according to control commands. And finally, for the smartphone interface, a mobile app with safe telemetry via secure Bluetooth or Wi-Fi displays EMG intensity, obstacle proximity, and system health, and enables task automation through voice or touch inputs. On the software side, the CNN decoder is trained on paired EMG datasets collected from healthy volunteers and stroke patients, performing standardized gesture protocols, concurrently a yo-yo-based division network classifies obstacles, pedestrians, furniture, stairs with combined radar and vision feeds. Sensor fusion combines radar and USP into a unified occupancy grid other than 30 Hz and configures thresholds tuned for safety. The mobile app built in React Native offers cross-platform compatibility and features customizable alert thresholds, user profiles, and integration with third-party services for e-commerce and telehealth. Hardware components include malware or Delphi surface EMG sensors and embedded NIF Jackson or C-Link's FPGA for low latency inference, TI-AWL radar for centimeter scale ranging, and Intel WaveSense for depth perception. Our model prototype have demonstrated an EMG decoding accuracy of 82% across 5 critical gesture clusters, which grab, raise over, and stop validated in model tests with both healthy and hemiplegic subjects modeled with computers. Obstacle detection and avoidance strategy consistently measures under 1000 milliseconds, successfully preventing 91% of simulated collision scenarios in a controlled corridor environment. In a model preliminary user study with potential chronic stroke survivors, participants achieved a 9.2% increase in unreached and grabbed workspace compared to using a passive base. Usability surveys indicate that 81% of users found the system intuitive and average down and off time was reduced to 55 seconds. This results affirm EDASR's potential to deliver reliable, safe assistance in real-world settings. Our 12-month development roadmap is organized into 4 phases. In month 1 to 2, you'll finalize system requirements, calibrate sensors in the lab, and refine EMG electrode placement protocols. Months 3 to 5 focus on AI model training, hardware software integration, and advanced validation of decoding accuracy and hazard avoidance, pilot deployments, and user feedback sessions occur in months 6 to 8 across multiple clinical and community settings, informing iterative improvements. And finally, months 9 to 12 are dedicated to manufacturing planning, large-scale manufacturing planning, safety certification, and regulatory compliance, and also comprehensive documentation. Our key performance targets include EMG decoding accuracy above 90%, obstacle detection latency under 100 milliseconds, at least a 25% gain in functional weeks of space, and overall system uptime of 99% or higher. In conclusion, the Electromyography-Driven AI assistive system for stroke rehabilitation represents a paradigm shift in post-stroke care, and by combining voluntary intent decoding, proactive hazard avoidance, and integrated daily life automation into a single modular platform, EDSR enhances patient safety, restores functional independence, and reduces caregiver burden. Its adaptable architecture supports both upper and lower limb applications, whether worn as a soft exosuit or mounted on a powered wheelchair. And future devices include integrating additional modalities such as speech and eye tracking, extending IoT control to home automation systems, and enabling tele-rehabilitation for remote clinicians to monitor and adjust therapy protocols in real time. Thank you for your attention, and we look forward to exploring how EDSR can transform neuro rehabilitation practice and improve quality of life for stroke survivors worldwide.